$10,000. That's not a typo. That's Tesla's actual target price for the Model 2, and it's already being built at 3,000 cars per day. 7 new updates are baked in: Porsche-inspired handling, Falcon wing doors, GigaCast frames that solved a 3-year vibration problem, and production tech so advanced it's outpacing Ford and GM combined. But here's the shocking part. How does a $10,000 EV get features that cost twice as much on competitors? And why is Tesla's line running 150% faster than anyone else's? The answers reveal a manufacturing breakthrough that's about to reshape the entire industry. Let's dive right in. Here's what should be impossible: a $10,575 car that handles like a Porsche 911 and looks like a Jaguar F-Type. Tesla didn't copy these legends. They reverse-engineered the feeling. They studied what makes a 911 grip corners with surgical precision and what gives an F-Type that confident glide. Then they scaled it down into a compact EV using what insiders call scaled dynamics. The numbers tell the real story. Tesla targeted 10 to 15% lower rotational inertia than competing compact EVs. That means sharper steering response without the twitchy nervousness that makes budget cars feel cheap. Weight distribution sits at 48 to 52% front to rear, almost perfectly balanced, achieved by positioning battery modules slightly rearward and adding precisely calculated ballast in the front subframe. This isn't guesswork. It's 55.1 pounds of strategic mass placement that changes how the car rotates through every turn. Tesla lengthened the wheelbase by 6 to 12 inches compared to typical compacts. Why? Longer wheelbase smooths highway rides for cross-country road trips, while short overhangs keep the car nimble in tight urban parking. They studied how Americans actually drive and built the dimensions around that reality. The suspension blends Porsche's progressive anti-roll geometry with Jaguar's multi-link comfort tuning. Spring rates reduced by 15%, anti-roll bar stiffness increased by 10%. The result? A car that feels tight on interstates but absorbs brutal potholes without jarring your spine. Aerodynamics hit a drag coefficient around 0.22 to 0.24, translating to 8 to 12% energy savings on highway drives. That's 8 to 12 extra miles of range on a 250-mile battery, enough to reach the next charger instead of calling roadside assistance. So, here's the question. If you had to pick one priority for a budget performance EV, what matters most? Steering precision, suspension comfort, or aerodynamic efficiency? Drop your answer in the comments. Falcon wing doors on a budget EV sounds like fantasy. The Model X nearly bankrupted Tesla, perfecting this mechanism. So, how did they engineer it into the Model 2 without demolishing the price point? Falcon wing doors provide 16 to 24 inches more shoulder clearance than conventional doors in tight parking spaces. For older passengers or anyone carrying groceries, that means less twisting and smoother entry. Tesla simplified the hinge architecture dramatically, replacing the Model X's multi-axis, fully motorized system with a hybrid mechanical counterbalance assisted by a single motor and over-center dampers inspired by aircraft door technology. This cuts motor torque requirements by 60% and reduces parts count by 40%. Component costs dropped further by swapping aerospace aluminum links for stamped high-strength steel covered in bonded composites, reducing cost per door by 30 to 45%. Each door weighs just 26 to 40 pounds through re-engineered skins and hollow structural reinforcements. The incremental cost per door? Low triple digits instead of thousands. Picture this. You're parked between two trucks at a crowded grocery lot, Arms full, maybe a sore back. You press a button and the door lifts up instead of swinging wide. No dents, no awkward squeeze, no stress. GigaCasting promised revolutionary manufacturing, casting entire vehicle sections in single pieces, reducing weight by 20%. But early Model 2 prototypes revealed a nightmare. Unusually stiff ride quality and strange shaking above 65 miles per hour that engineers couldn't diagnose for 3 years. The culprit? Microscopic inconsistencies in the aluminum alloy? Uneven composition created local stiffness variations. Sections that were 2% harder than designed acted like rigid plates, transmitting road shock straight into the cabin. Tiny air pockets trapped during casting flexed differently from solid metal, creating resonance at highway speeds. Tesla's solution was surgical. They controlled every critical element in the aluminum alloy within plus or minus 0.5% tolerance. Vacuum-assisted die casting with directional solidification eliminated porosity, reducing air voids in high-stress zones from 1 to 2% down to 0.2%. Post-cast heat treatment normalized grain size and relieved internal stresses, keeping dimensional changes under 0.020 inches, tighter than a human hair. Targeted structural reinforcement added high-strength steel inserts at only 10 to 20% of the underbody, precisely where bending and torsion concentrate. Elastomeric isolators and tuned mass dampers at key nodes cut vibration amplitude by 70% in the 20 to 30 Hz range, the exact frequency humans feel most uncomfortably at highway speeds. Defect rate for critical areas? Under 1 per 10,000 parts versus 1 in 500 for traditional stamped assemblies. Pothole guard. Uses front cameras scanning at 60 to 120 frames per second with vibration sensors. Within 10 to 15 milliseconds of detecting a pothole, the system softens damper stiffness and reduces region braking. Peak impact acceleration drops 20 to 40%, reducing tire and rim damage by 30 to 50%, saving $250 to $1,200 across 3 to 5 years. Storm vision. Applies nanohydrophobic coating and microheaters to camera lenses, clearing droplets in 0.2 to 0.4 seconds and fog in 5 to 8 seconds. In moderate rain, blurred frames drop 60 to 70%. At 60 kilometers per hour in light rain, automatic braking identifies obstacles earlier, trimming stopping distance by 1 to 2 meters. Adapter-less fast charging. Integrates protocol detection directly in the inlet, auto-detecting CCS, NACS, or IEC Type 2 in 2 to 4 seconds. Peak power hits 200 to 250 kilowatts, ramping 30 to 40% faster than adapter setups. On a 600-kilometer trip, this saves 10 to 14 minutes of charging time. Predictive wear pack. Uses microphones and accelerometers to detect brake and tire wear patterns, estimating tread depth within 0.5 millimeters. Timely rotations extend tire life 10 to 20%, saving $60 to $180 per cycle. Early pad replacement avoids $300 to $600 rotor warping. Total savings over 3 to 5 years, $300 to $900. Right to repair mode. Provides step-by-step procedures, torque specs, and diagnostics through the touchscreen, cutting troubleshooting time 20 to 40%. Fixing a stuck window motor drops from 2 to 3 hours to 45 to 60 minutes, saving $150 to $300 in labor. UWB anti-theft. Measures radio pulse travel time, verifying proximity within 10 to 30 centimeters in under 10 milliseconds. If stolen and cellular is cut, the car emits encrypted UWB pings that nearby Teslas relay to the cloud, extending search range from tens to hundreds of meters. Coro Shield applies 3-layer treatment, showing 720 to 1,000 hours salt spray resistance, 2 to 3 times better than standard paint. Smart drains trigger when moisture exceeds 85% for 30 minutes, preventing corrosion and saving $80 to $100 per service visit. Tesla's production line runs at 3,000 vehicles daily, 900,000 yearly. Ford's F-150 Lightning manages 1,000 daily. VW's ID.4 hits 850. GM reaches 1,200. Tesla outpaces the next largest by 150 to 200%. The enhanced GigaPress operates at 6,500 tons, eliminating 220 weld spots per vehicle. Defects dropped 62%. Material yield hit 97% versus industry's 82%, saving $750 per unit. Then there's 850 ABB robots with 9-second tool changes, handling 16 variants per shift. First pass yield exceeds 99.7% versus Ford's 98%, VW's 96%, GM's 97%. Cycle time? 7.5 hours from chassis to finished vehicle versus industry's 12 to 14 hours, a 45 to 50% reduction. Material scrap stays below 0.8% versus 2 to 3% in legacy lines. Energy consumption drops 18% per vehicle. One operator oversees 12 robots versus 5 to 6 in traditional plants. Modular cells switch between variants in under 1 hour, while competitors need up to a year reconfiguring plants. This system replicates globally, cutting setup costs 25 to 30%. Can Ford, GM, or VW catch up before Tesla's lead becomes permanent? Drop your prediction below. So here's what it all means. Tesla just proved that affordability doesn't require compromise. The $10,000 Model 2 isn't a stripped-down budget EV. It's a complete reimagining of what's possible when engineering precision meets manufacturing innovation. 7 updates that shouldn't exist at this price point. Production speeds that leave legacy automakers scrambling. And a structural integrity problem solved after 3 years of relentless iteration. This is exactly why Tesla keeps widening the gap while others make excuses. But this goes beyond one vehicle. What we're witnessing is the blueprint for the next decade of EV manufacturing, when Tesla can replicate this production system globally, cutting setup costs by 25 to 30% and switching variants in under an hour. The entire industry faces a choice: adapt or become irrelevant. The Model 2 launches in approximately 7 months, and by then, competitors will still be figuring out how to match today's specs, while Tesla's already engineering what comes next. And this is just the beginning. The production infrastructure is operational, the manufacturing breakthroughs are validated, and the supply chains are shifting in real time. What happens when this system scales to multiple gigafactories worldwide? What does transportation look like when a $10,000 electric vehicle outperforms vehicles costing twice as much? What do you think will be the biggest challenge for Ford, GM, and VW in catching up? And which of these 7 updates would make the biggest difference in your daily driving? Drop your thoughts below. The discussion is just getting started. This is Tech Revolution, and we dig into the breakthroughs reshaping how we move, build, and innovate. If analysis like this helps you stay ahead of the curve, you know where to find us for the latest developments. The future of affordable transportation isn't coming. It's already being built at 3,000 units per day. And that changes everything.